every terrifying way the universe could end. Yeah, not just our planet, but the entire cosmos has an expiration date, and scientists have mapped out exactly how it's all going to go down. Right now, the universe is expanding so fast that galaxies are literally disappearing from our observable horizon forever. But here's the twist. Physicists believe the universe could spontaneously destroy itself through vacuum decay. We'd never see it coming as the death bubble travels at light speed, erasing everything and rewriting physics itself. We're not talking about asteroids or solar flares. That's child's play. We're discussing the death of everything that has ever existed. Until a century ago, Einstein himself thought the universe was eternal, adding his cosmological constant to keep it static, later calling it his biggest blunder. Today's cosmologists have given us multiple endgame scenarios based on solid observations from our most advanced instruments. Get ready to explore, space enthusiasts. Let's start with what most cosmologists consider the most likely scenario, the heat death, also known as the Big Freeze. Now, don't let the word heat confuse you. This is actually about the universe reaching maximum entropy, a state of perfect disorder where no more work can be done. Picture this. You're at a party, and everyone's dancing, music's pumping, energy is flowing everywhere. That's our universe right now. Stars fusing hydrogen into helium, galaxies colliding and merging, black holes consuming matter and releasing jets of radiation. But every party winds down, and when this cosmic celebration ends, it concludes not with fanfare, but with absolute stillness. The heat death is rooted in the second law of thermodynamics, which states that entropy in an isolated system always increases. Right now, we have pockets of low entropy, stars, planets, living organisms, but these are temporary islands of order in an ocean of increasing disorder. Think of it like a drop of ink in water. It starts concentrated, but inevitably spreads until it's evenly distributed. According to calculations by physicist Fred Adams and astronomer Gregory Laughlin, star formation will cease entirely in about 10 to the 14th power years, 100 trillion years. The universe will have converted all its available hydrogen into heavier elements. The last stars will be red dwarfs, with masses less than 0.25 times our Sun, capable of burning steadily for up to 10 trillion years, nearly 1,000 times the current age of the universe. When these final stars die, we enter what cosmologists call the degenerate era, dominated by white dwarfs, neutron stars, and black holes. But even these aren't permanent. Through a process called Hawking radiation, where quantum effects near the event horizon cause black holes to slowly evaporate, even the most massive black holes will disappear. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate completely, while supermassive black holes could last up to 10 to the power of 100 years. The controversial aspect that divides physicists involves what happens in this maximum entropy state. Roger Penrose, who shared the 2020 Nobel Prize in Physics, proposes conformal cyclic cosmology, where the infinitely expanded, cold universe becomes mathematically identical to the hot, dense conditions of a Big Bang, potentially starting the cycle anew. However, most physicists remain skeptical, arguing that Penrose's model requires specific conditions about particle physics that we haven't verified. Hey, if you're enjoying this cosmic horror show so far, hit that subscribe button and ring the notification bell. Because trust me, you don't want to miss what's coming next. We're about to explore scenarios that make science fiction look tame. If the heat death is like watching a fire slowly burn out, the Big Rip is like watching reality itself get pulled apart at the seams. This scenario depends entirely on the nature of dark energy, that mysterious component making up approximately 68% of the universe's energy density. Dark energy's defining characteristic is its negative pressure, causing space to expand at an accelerating rate. We've confirmed this acceleration through multiple independent observations, including type Ia supernovae studies that earned the 2011 Nobel Prize in Physics. But what if dark energy isn't constant? What if it's what physicists call phantom energy, where its density actually increases as the universe expands? Robert Caldwell, who coined the term Big Rip in 2003, calculated that if dark energy has an equation of state parameter W less than -1, meaning its negative pressure exceeds its energy density, the universe faces a finite time singularity. The expansion rate becomes infinite at a specific moment in the future. The timeline Caldwell proposed, assuming W equals -1.5, gives us approximately 22 billion years from now. Though this number is highly sensitive to the exact value of W current measurements from the Planck satellite and other observations constrain W to be very close to -1, with error bars that don't strongly favor the Big Rip scenario. In this scenario, the destruction unfolds hierarchically based on binding energies. Approximately 60 million years before the end, galaxy clusters would disperse as the expansion rate exceeds their gravitational binding. 3 months before the end, the Milky Way would disintegrate. The Earth would be torn from the Sun's orbit just 30 minutes before the final moment. And in the last nanosecond, atoms and then subatomic particles would be ripped apart as the expansion rate approaches infinity. What makes this particularly unsettling is that we could potentially see it coming. Unlike vacuum decay, we'd watch the universe gradually accelerate its expansion, see distant galaxies disappear faster, and know our fate was sealed. Now let's examine the Big Crunch, the scenario where gravity eventually reverses cosmic expansion, pulling everything back into a reverse Big Bang. This was actually the favored model among cosmologists until the late 1990s. The physics here is straightforward. If the universe's average density exceeds a critical value, about 5 hydrogen atoms per cubic meter, gravity should eventually halt and reverse the expansion. We call this critical density parameter omega. If omega is greater than 1, we get a Big Crunch. For decades, measurements suggested omega was close to 1, keeping the Big Crunch viable. But the 1998 discovery that expansion is accelerating, not decelerating as gravity alone would cause, essentially ruled out this scenario under standard cosmology. The universe's density, including dark matter and dark energy, appears to equal exactly the critical density, but dark energy's repulsive effect dominates. However, Paul Steinhardt at Princeton and Anna Ijs have developed cyclic universe models where dark energy could be dynamic. In their ekpyrotic model, from the Greek ekpyrosis, meaning conflagration, the universe undergoes infinite cycles of expansion and contraction. Each cycle lasts roughly 1 trillion years, with the contraction phase creating conditions that trigger a new Big Bang. The key insight is that a Big Crunch doesn't necessarily mean everything returns to a singular point. In brane cosmology, derived from string theory, our 3-dimensional universe could be a membrane, brane, in higher dimensional space. A Big Crunch might represent our brain colliding with another, creating what appears to be a Big Bang to inhabitants of either brane. Recent observations of gravitational waves and cosmic microwave background polarization could potentially test these cyclic models, though current data doesn't support them over standard cosmology. Still with me? Good, because we're only halfway through our tour of cosmic endings. If you're finding this as fascinating as I am, drop a comment below with which scenario you find most plausible. And hey, sharing is caring. Send this to that friend who loves debating physics over coffee. This is the scenario that particle physicists lose sleep over. Vacuum decay, also called false vacuum collapse. It's perhaps the most unsettling possibility because it could begin literally anywhere, at any time, without warning. The concept centers on the Higgs field, discovered in 2012 at the Large Hadron Collider. This field permeates all of space and gives elementary particles their mass through their interactions with it. We assume the Higgs field sits at its minimum energy state, the true vacuum. But quantum field theory allows for the possibility of metastable states, local minima that appear stable but aren't the absolute lowest energy configuration. Think of it like a ball in a valley on a mountainside. The ball seems stable, but there's an even lower valley beyond the ridge. With enough energy, or through quantum tunneling, the ball could cross that ridge and fall to the truly lowest point. If our vacuum is false, a quantum fluctuation could nucleate a bubble of true vacuum. Joseph Lycan, a theoretical physicist at Fermilab, calculated that based on the measured masses of the Higgs boson, 125 gigaelectron volts, and the top quark, 173 GeV, our universe sits right at the boundary between stable and metastable, what physicists call critically stable. This bubble would expand outward at the speed of light, fundamentally altering the Higgs field value inside it. Since particle masses depend on the Higgs field, chemistry as we know it would be impossible in the bubble. Protons and neutrons might not even be stable. It wouldn't be destruction in any conventional sense. It would be a complete rewriting of physical law. The timing calculations vary wildly. If the universe is metastable, the expected lifetime before vacuum decay ranges from 10 to the power of 100 to 10 to the power of 500 years, far longer than any other timescale we've discussed. But quantum mechanics means there's always a non-zero probability it could happen tomorrow. Some physicists worried that high-energy particle collisions could trigger vacuum decay. However, cosmic rays routinely create collisions at energies millions of times higher than our best particle accelerators, and Earth has survived 4.5 billion years of such bombardment. If we could trigger vacuum decay, nature would have done it already. Recent observations have opened an intriguing possibility. Dark energy might not be constant. The Dark Energy Survey, completed in 2019, and other projects have found hints, though not conclusive evidence, that dark energy's strength may have varied over cosmic history. If dark energy is dynamic, what physicists call quintessence after the classical fifth element, its behavior could change dramatically over time. Some models suggest dark energy could weaken, strengthen, or even change sign, becoming attractive rather than repulsive. The quintom scenario, proposed by physicists at the Chinese Academy of Sciences, involves dark energy oscillating between positive and negative values. During positive phases, the universe expands. During negative phases, it contracts. Unlike the regular cycles of the ekpyrotic model, these oscillations would be chaotic and unpredictable. Early results from the Dark Energy Spectroscopic Instrument, DESI, released in 2024, show tantalizing hints that dark energy might have been stronger in the early universe. If confirmed, this would revolutionize cosmology and make the universe's fate far less certain than we thought. String theory and eternal inflation models suggest our universe might be one of countless bubbles in an eternally inflating multiverse. If true, these universe bubbles could collide, with catastrophic consequences for both. This isn't pure speculation. Matthew Johnson at the Perimeter Institute and colleagues have identified circular patterns in the cosmic microwave background that could be signatures of ancient collisions during our universe's infancy. 4 such candidate spots have been identified, though the statistical significance remains debated. In a collision, a domain wall would propagate through our universe at nearly light speed. On one side would be our familiar physics, on the other, potentially completely different physical laws. The wall itself would be a region of extreme energy density, where neither set of laws functions properly. The probability of such a collision is thankfully considered extremely low, but in an eternal inflation scenario with infinite bubble universes, Even unlikely events become certainties given enough time. Neil deGrasse Tyson captured the humbling nature of these cosmic mysteries when he said, "The universe is under no obligation to make sense to you." But he also offered this perspective on our role. We are part of this universe. We are in this universe. But perhaps more important than both of those facts is that the universe is in us. Let's examine the slowest possible ending, proton decay. While we've never observed a proton decay, many grand unified theories predict protons have finite lifetimes, just incredibly long ones. Current experiments, particularly Super Kamiokande in Japan, have pushed the lower limit for proton lifetime beyond 10 to the 34th power years. Some theories suggest lifetimes of 10 to the 36th power years or longer. These numbers are so vast that the current age of the universe, 13.8 billion years, is negligible in comparison. If protons decay, all baryonic matter, everything made of atoms, eventually disintegrates into lighter particles like positrons and pions, which further decay into photons and neutrinos. The universe would slowly forget how to be matter, leaving only an increasingly dilute gas of fundamental particles. This process would be so gradual that civilizations could theoretically adapt, perhaps encoding themselves in the quantum states of photons or the patterns of neutrinos. But eventually, even these would disperse into the expanding void. Understanding potential cosmic endings isn't just academic exercise. It reflects our deepest understanding of physical law. Each scenario emerges from established physics. Thermodynamics predicts heat death. General relativity allows big crunches. Quantum field theory permits vacuum decay. These investigations have practical implications. Studying dark energy's nature could reveal new physics. Understanding vacuum stability helps us grasp why the universe's constants have their specific values. Searching for evidence of other universes pushes our observational techniques to their limits. Moreover, contemplating cosmic mortality offers perspective on our moment in the universe's history. We exist in what cosmologists call the stelliferous era, when stars shine and planets orbit and life is possible. This era represents perhaps 1/10,000,000th of the universe's potential lifetime, yet it contains all of history, all of life, all of human achievement. Look, I know this has been heavy stuff. We've journeyed from heat death to the big rip, from the big crunch to instant vacuum decay. But here's what's remarkable. You're now among the tiny fraction of humans who understand these ultimate cosmic possibilities. If you've made it this far, you're clearly someone who doesn't shy away from the big questions. So hit that subscribe button and ring the notification bell. We explore cosmic mysteries every week, from black holes to quantum mechanics. And if you enjoyed contemplating the end of everything, you'll love what's coming next. Drop a comment below. Which ending seems most plausible to you? And share this with that friend who stays up late watching space documentaries. Remember, we may be fleeting arrangements of particles in an expanding cosmos, but we're arrangements capable of comprehending our own existence. Right now, we're here. We're conscious, and we're unraveling these mysteries together. Until next time, keep looking up. Stay curious, space fans.